Welcome to my classroom. In this fuel cells and batteries course, we have been discussing about direct methanol fuel cells in the previous lecture. In this lecture, we are going to discuss about properties of membranes. Particularly, we will focus on Naphtha membrane and its properties, and we will look into a case study of if a new membrane is prepared, what are the tests that has to be conducted to compare it with the performance of Naphtha membrane, and if time permits, we will look into the limitations of low temperature PEM fuel cells. Ready? Direct methanol fuel cells have been commercialized. You can see some of the cellular mobile phones. You can see the Motorola models, Samsung model, Toshiba model phones, which use direct methanol fuel cell as the battery in place of batteries. Okay, and if you look at even these smart fuel cells, if you look at the specifications, you can see that here you can see that. So you have continuous output power of 25 watts maximum, 12 VDC output voltage, 12 volt. You have operating temperature of 40 degrees Celsius and the dimensions are given. You can see that 12 centimeters, 16 into 17 centimeters. And fueling is replaceable tank cartridge. It can be exchanged during the operations. And weight of the cartridge is around 190 grams. And check it in smartfuelcell.de. Okay. So these are some of the prototypes developed by the smart fuel cells, and we have seen in detail about what is a direct methanol fuel cell in the previous lecture, where what is the fuel here. It is not the hydrogen and oxygen are not being sent here. Here in place of hydrogen, we are directly sending methanol as the fuel. Okay, so we are sending methanol and water in the anode side. There are two raw materials or feed reactants that are being sent in the anode side, that is methanol and water, and in the cathode side we are supplying oxygen as usual. Okay, so in the anode side you have CO2 formation and some amount of water is used. That water also will pass through this membrane. You are going to have H plus ion passing through the membrane, and you have that water is being sent out through the flow field. So water, H plus ions, oxygen combine to form the product at the cathode side. Okay, so water is being formed in the cathode side also. Okay, so if you look at some of the technological limitations and the challenges ahead, you have pure electrode kinetics are there, large activation work potential needs to be done. We have discussed this about activation potential, polarizations in the thermodynamics of these fuel cells. So you can see that at least 200 to 300 millivolt of cell voltage is being lost. So we want to develop good catalyst for such minimizing this kind of activation polarization. That is, we want to have a more effective catalyst which will minimize this activation potential losses, polarization losses. So where we are at least losing 200 to 300 millivolt of the voltage of cell voltage being lost, right? So that way, that is one area people focus on. So if you want to do some work in this fuel cell area, you can look into good catalyst development for this particular direct methanol fuel cell. And even if you look at the, for interest, good mass transfer studies, all that, if you look at the mass transport, we want to have, there is CO2 rejection has to be there, low methanol concentration has to be used. So we want to have a good electrode structure which will not allow the methanol crossover being taking place in the membrane also, right? So that's all this membrane preparation, electrode material development, all that is a big challenge, because in this also, because of this electrode structure, there is a loss of around 25 to 150 millivolt of voltage is being lost. Okay, so that way development of a good electrode material also is a need of the hour. Okay, so that's what we have seen in the previous lecture. So in this lecture, we will discuss about membrane properties for PEM fuel cells. So you know that coming to this course, we know that the world is more focused on developing alternative energies from the renewable sources, because all these fossil fuels are being consumed faster rate. Okay, so they are not only limited in quantity available, but they are also causing environmental concern, right? We have seen in detail about the global warming, what is the effect of that, all that, right? So fuel cell is one of the promising and sustainable technology for generating clean energy. And in that we have been focusing on this PEM fuel cell, that is polymer electrolyte membrane fuel cell, which is one of the most pioneering among the all type of fuel cells. See, we have high temperature fuel cell like molten carbonate, all that we are going to discuss later. But at low to medium temperature, if you look at the low temperature operations, PEM fuel cell is more prominent among the other type of fuel cells. Okay, so under the even PEM fuel cells, we have dedicated a separate lecture for this direct methanol fuel cell, because that is more attractive, because they are lightweight, they are compact in design, their moderate working temperature is enough, they're high, they have high energy density, and in place of hydrogen, we can even use methanol as the fuel. So that's why we have focused on direct methanol fuel cell in the previous lecture. Okay. Remember, in this in your fuel cell, this membrane, proton exchange membrane, is an essential component in the DMFC, which will directly influence the performance of the fuel cell. Okay, so that's why we are going to focus particularly about the membrane which is being used in the fuel cells. Okay, and if you look at the various membranes available, Naphtha is the most widely used membrane, but it is also having some limitations. Okay, so there is high methanol permeability is there. We have to reduce the methanol crossover, which we have discussed in the previous lecture also. And the cost of Naphtha, because it is a monopoly by the company, we DuPont, the cost is high and it is more sensitive towards the temperature. Okay, any research towards developing a membrane will have this Naphtha as the reference. Okay, so that's why worldwide researchers are also attempting to alternate the membrane, either by developing a completely new membrane or making a blending of something with by modifying the Naphtha membrane. Okay, so for example, Naphtha can be modified by combining with carbon nanotubes, carbon nanofibers. Okay, or you can use chitosan based biopolymers can be used. You can use hydroxide, ceramic oxides, oxoacids, some incorporate some metal oxides like titanium oxide, zirconium oxide, or you can include some silica, zirconium phosphate, and heterofolate acids. All these can be combined, incorporated into the membrane. That is modification of Naphtha membrane. So that can be done using some filler materials, which will enhance it. The synergistic effect of combining two material should have a positive effect, right? If you add this and the performance is not significantly increasing, there is no point in use doing that, right? So that way, so any incorporation needs to be studied and the performance has to be compared with this reference membrane, which is a Naphtha membrane. That's why we are going to focus on Naphtha membrane, because we work on a new membrane development and you see that the performance is improving, then we have done some considerable contribution to the scientific society. Okay, so there are various modification methods are available. Among that, this composting, cross-linking techniques are most reliable method, by which is also contributing in suppressing the methanol crossover. Okay, so that is why it's important to go for these modification methods like composting method and cross-linking techniques, which is not in our area. That actually in membrane course we will be learning different methods of doing that. Okay, so ultimately what we are trying to do, we are increasing the mechanical strength, we are trying to reduce the methanol crossover. Okay, so that is what we have been doing. And what we can do incorporation, in the incorporation we can introduce the naturally available polymers like chitosan modified with zeolites, polyacrylic acid. All of them, when you incorporate into Naphtha membrane, they increase the barrier to the migration of this methanol. So that way, the methanol permeability is being reduced. Okay, so that way, but thing is, there are several membranes which will block the methanol crossover. But what about the ultimate main aim is to conduct the protons, right? So without compromising the properties of proton conductivity, we have to reduce the methanol crossover property. That is the challenge in preparing a alternate membrane in place of Naphtha for the fuel cell applications, particularly in PEM fuel cells or in direct methanol fuel cells. Okay, so that way, this partially fluorinated membranes, when you modify with this PVD, that is a polyvinylidene fluoride, sulfonates or phosphonate membranes, they also show barrier to, that is what the methanol crossover is reduced, but they are showing some fuel cell efficiency decrease. Okay, so they are showing some inferior fuel cell efficiency. Okay, and what about non-fluorinated membrane? The non-fluorinated membranes such as vinyl polymers, phenol formaldehyde, cation exchange membranes also showed stability wise they have issue, so they show less mechanical stability, and there is a problem of swelling of the membrane. That is what overloading of water, more water consumed in the membrane, they try to bulge out, right? So that way. And we have even seen the cost of the PEM fuel cell stacks is predicted to be around in 1990s. It is being predicted as 2009 it has been predicted as $40 per kilowatt. Okay, so now if I just searched for any 2018 paper or 2020 any cost prediction is being done, so we come up with this paper. So this is the analysis report given by Fuel Cell Technologies Office of US Department of Energy, prepared by Gregory Klein and Eric Parker. So what they have made a prediction calculation is in 2018, 20 and 2025. The prediction is for 2025. Okay, so based on 18, 20. So what they have seen is when it is a function. Okay, so what is the dollar rate per kilowatt is based on what bulk quantity you produce, right? When you prepare something in small quantity, you are not going to have that cost reduction. So when you are able to have annual production is being like this increases, we can see that fuel cell cost can be reduced down. Okay, so that is a prediction there. As I told you, it was around $40+ per kilowatt. Now it is predicted by 2025, when you are doing large annual productions, we can reduce that to $38.34 per kilowatt. So that is what have been reported by the US Department of Energy. So that is the cost of energy when we are using this direct methanol fuel cell systems or PEM fuel cell systems. Okay, and if you look at, I had told you we are going to discuss in detail about various type of Naphtha membrane which is being researched out. Okay, as I said, in place of pure Naphtha, people try to do research by incorporating some other material onto it, right? It can be metal oxide, it can be polymer, it can be biopolymer, right? So that way. So if you look at the different membrane systems and what is their effect on ionic conductivity is given in this table. Please look into this in detail. So I'll just read out one of them. So if you look at Naphtha incorporated with carbon nanotubes, what we observe is there is an improved conductivity and mechanical strength, which leads to the better PEM fuel cell performance. Okay. And when you use this silica is added, what is happening? Conductivity is slightly lower to Naphtha in high relative humidity condition. Improved conductivity is there at elevated temperatures and lower relative humidity values. Okay, so here RH represents relative humidity. Okay. So you can look into what different materials are incorporated into Naphtha and what is the impact on the ionic conductivity. Okay. So now in this lecture, we will focus mainly on the membranes. So we will look into what is, first we will recall what are the functions of a fuel cell. We will look into first law of fuel cell, equivalent weights of membrane, what is water uptake, water activity, solubility, diffusivity, permeability, what is barrier unit, what is the rate of permeation in different unit, current density units, what are the 4 basic modes of transport in membrane, what is Darcy's law, what is Schrodinger's paradox, hydraulic permeability, and we'll try to solve numericals in the next few lectures. Okay, so in this I will try to cover the maximum in this some of the objectives here. Okay, let us start with the introduction. Will you just note down here 1, 2, 3, 4 up to 9 is there, right? So we know that a particular any fuel cell will contain a membrane. PEM fuel cell mean it will have a membrane, polymer electrolyte membrane, then you have electrode, then you are having and bipolar plates collector, then you have bipolar plates which also it is connected to current collector, that is anode side, it is anode current collector. In cathode side we have cathode current collector. Now you should be able to say what are the steps involved in the function of a fuel cell. What is happening in one? So you are having 2 sides here, right? So here it is 1, something is entering, here is 1. So there are raw material entering into there, right? So what is the step there? What is that one? Then second something is happening, then 3 something is happening, 4 something is happening, and 5 something is leaving, 6 something is happening, and 7 something is happening, you have 8 something happening, and 9 something is leaving. So we should be able to label all these steps now. Okay, so please try to write it down on your own. What is happening in this system? Take 2 minutes time. try to recollect all the concepts that we have discussed, what is happening, what is actually happening in this fuel cell in the function. So it's a surprise test. You should be able to write it on your own. Okay, because after this many lectures, you should know what are the steps involved in the functions of a fuel cell. Okay. Now, what is the first step here involved? That is, hydrogen has to get into this, flow through these bipolar plate channels, right? So there is a gas flow through the channels. So what is that? Some convective flow may be induced in the porous layers of the membrane electrode assembly also. Then there is a gas diffusion. Two is diffusion through the electrode. What is that electrode? We have MEA, right? Membrane electrode assembly. So gas diffusion through the porous media. That is the second step. First step is gas is passing through the channels present in the bipolar plates. Okay. Number two is gas is diffusing through the porous media and it is reaching the catalyst surface. So once it reaches the catalyst surface, there will be adsorption taking place. Some electrochemical reaction will be taking place at the anode and cathode, right? So step 3 is both sides, either it is anode side or cathode side. 1 and 2 are same. This side it is going to be hydrogen, that side it is going to be oxygen, right? So 3 is the electrochemical reaction taking place at the thing. What is 4? Either it will be proton is passing through. 6 is anything other products may be there that will be passing through. So that we have to see depending upon the stage. It may be, if it is hydrogen oxygen system, I have given you hydrogen as the feed, right? So obviously 4 is nothing but proton transport through the proton PEM fuel, PEM membrane. Okay, so that is what is a step 4. What is step 5? Something is leaving. What is that? Reaction is taking place at 3. When H plus ions are going this side, what goes through the external circuit? It is 5. That is the electrons. Electron is passing through electrically conductive cell component, which is called collector plates. Okay, so anode collector plate, there is cathode collector plate will be there on that side. Okay, so then sixth step. Then what is the sixth step there? I'll come to it. What is the sixth step? There will be water transport through the polymer membrane, including both electrochemical drag and back diffusion, because that is where initially water formed that will go and saturate the membrane, right? So there is the diffusion of water taking place. And what about 7? 7 is like product formed water will be leaving the system. So 7 is water transport to the porous catalyst and the gas diffusion layer as the product going out. What is 8? It is again two-phase flow of unused gas carrying water droplets. So you are going to have all the product formed or by unreacted reactants will be leaving the system. And what is the 9th one? It is the heat. Heat is represented this way. So 9 is the heat transfer, both the conduction through solid components and convection to the reactant gases and cooling medium also. Remember, these bipolar plates will have cooling water into it. Okay, so we should know about these 9 steps that are involved in this one. And coming to altering the property, because when it comes to research now, we try to modify some property. We should start with this one. You cannot have all positive impact. Okay, so because we'll look into this first fuel cell law. What is first fuel cell law? Although a fuel cell seems to be a very simple device, numerous processes take place simultaneously. We have seen heat transfer, mass transfer, we have seen reaction taking place, we have seen current passing through it, we have seen electron passing through the external circuit. Okay, so they all taking place. Some if a foreign particle are there, it is going to poison some other unwanted, undesired reactions may take place. Okay, so that's why it is important to understand those processes. The mutual interdependence. One, if you change the temperature, it will have impact somewhere. When you change the membrane thickness, when you change the flow rate, okay, so when you change the purity of the hydrogen and oxygen, it is going to have the impact. Okay, so they're dependent on the component design and material property should be known very well when you want to understand the process. Okay. Now you look into this first fuel cell law. So one cannot change only one parameter in a fuel cell. Remember, when you are changing one parameter in a fuel cell operation, okay, it will cause a change in at least 2 other parameters, and that among the 2 parameters, one is going to have an opposite effect. That means negative impact. You are increasing something, thinking that I am increasing another parameter increase. there is a third parameter which will go decreasing. So that way it is a trade-off between the parameters. Okay, so when you are changing something, that's what first fuel cell law we should know. We cannot change only one parameter. If you are changing one parameter, it will have impact on other two parameters, out of which one is going to be a negative one. Okay, that is the opposite effect we are going to have. Okay, getting close into this Naphtha membrane. So we are looking into this Naphtha membrane, which we are going to make use as the close one. Okay, so actually this Naphtha membrane is a product which came after your Teflon. Okay, initially the Teflon was the again a branded one, which is widely being used in many places. Okay, so what is Teflon? This is essentially we are going to make use of this Teflon. Okay, and what this Naphtha is, these membranes for PEM fuel cells are made of perfluorocarbon sulfonic acid, perfluorocarbon sulfonic acid ionomer. So that is the ionomer here. So this is what is that perfluorosulfonic acid, perfluorocarbon sulfonic acid. It is essentially a copolymer of tetrafluoroethylene (TFE) and perfluorosulfonate monomers. So from these two monomers, tetrafluoroethylene and perfluorosulfonate, a polymer is being made, a copolymer is being made, that is called perfluorocarbon sulfonic acid ionomer. So that is what we calling it as a brand name Naphtha membrane, because this is the commercial name Naphtha membrane, which is again made by the company DuPont. And they are using perfluorosulfonyl fluoride ethyl propyl vinyl ether. Okay, so that's what they are using to make this Naphtha membrane. Okay, so this is the structure of the Naphtha membrane. You can see that, and some functional group is attached here. What is the sulfone? As the name indicates, that's why that membrane is getting that name, perfluorocarbon sulfonic acid. Okay, so what is the functional group attached here? We should know. So here and HSO3 group is attached at the end of this polymer. Okay, so in this structure, sulfonic acid group is attached. What is that? S double bond O, single bond OH. Okay, so this is the structure of a Naphtha membrane. So if you look at this Naphtha membrane, which is being widely marketed by Sigma Aldrich, which is now called as Merck company. Okay, so Merck is the brand which is supplying you this Naphtha membrane in India. So if you look at the cost of this Naphtha membrane, you can see how much it costs. So there are different type of Naphtha membranes available. You can see here some number is given, right? 11, 7 is there. So that 11 and 7 represent something which we will discuss in detail. Just to show you the price of this particular membrane, Naphtha 117, its cost is around 49,694. In 2022, what is the price? The revised price is around 70,000 each. Yes. If you look at this Naphtha membrane name, we have seen now 117. So out of curiosity, we will come to know what is that 117 represents. Which Naphtha membrane we have to order if you want to make a PEM fuel cell. Okay. So these Naphtha membranes come extruded in different sizes and thickness. So they are marked with a letter N followed by a 3 or 4 digit number. Okay, and you can see that N117 like that, right? So we are going to see that number, 3 or 4 digit number we are seeing. Whether 2 digit means what does it mean? 3 digit means what does it mean? We will look into it. Okay, so that's important. So you can see that these are some of the widely used Naphtha membranes marketed: N115, N117, and N1110. So what is this 3 digit? Here the third and fourth digit is there. First 2 digits are there, right? So what does it mean? I will let you know. So I showed you what is Naphtha 117 cost. Okay, here 11 represents and 7 represents something. 11 represents the equivalent weight, 7 represents the thickness. How? We will see into it. So the first 2 digits are equivalent weight divided by 100. For example, when you say Naphtha 117, their equivalent weight is that first 2 digit multiplied by 100. So that way its equivalent weight is 1100. So that's what this first 2 digit is obtained by dividing by 100. Equivalent weight divided by 100, we get the first 2 digits. So equivalent weight is 1100. What if equivalent weight is 2200? So So for here we are going to have Naphtha 2,2. So such thing is not there. And just for example, I'm giving. Okay. So equivalent weight is 1100 means 1100 divided by 100, 11. So that is the first 2 digit represent. Okay. So you can see that we are having other thing also. 1500 is there, 1100 is there, 700 is there, 07 is there. Okay. So the equivalent weight, 3 equivalent weights are widely available: 1500, 1100 and 700. So what will be the Naphtha number? If it is if equivalent weight is 700, it is going to be 700 divided by 100, it is 7, right? So 2 digit instead of 2 digit, we are going to have only 1 digit there. Okay. And if it is 1100, 1100 divided by 100 is 11. If it is 1500, you are going to have 15 as the first 2 digit. Understood? What are the first 2 digits in this Naphtha membrane thing represent? Okay, now coming to the third point. What is the third digit? 7 is there now. So what is it having is, that is the thickness in mils. 7 mil thickness. So 7 represents 7 mil thickness. 5 represent 5 mil thickness, 10 represent 10 mils thickness. Okay, you know the conversion. So 7 mil is equal to 0.178 millimeters. Okay, so accordingly you can convert to 10 means how much, 5 means how much, and write. Okay, and even there are further versions of these Naphtha membranes are available, because for increasing the stability, they are treated with some chemicals. Okay, so in that case, instead of these 11, 11, all that, now they start with the 21, 22, because when you change that chemically stabilizing it, so the equivalent weight is altered. So you have NR211, NR2212. So this first 2 digit represents their equivalent weight. Okay, so that one are chemically stabilized ones. Okay, so when you have 1, it represents 1 mil thick, 1, 2, it represents 1 to 12 mils thickness. Okay, so that way, the third and fourth digit represents the thickness. Okay, so if Naphtha is available in several thickness, what is 1 mil conversion? 1 mil equal to 1 by 1000 inch, that is 0.001 inch, which is 0.0254 mm, which is 25.4 micrometers mu. Okay, so can you fill this table now? So mils these are the different mils of Naphtha membrane available: 2, 3.5, 5, 7, 10. What is the corresponding micrometer? You should be able to calculate and write it as well. Okay, so please write that. So for 7, what is the corresponding micrometer? 177.8. Okay, now equivalent weight of the polymer membrane can be expressed by the following expression. It depends upon your number of TFE groups on an average in the per PSE-PVE membrane. What is PSE-PVE membrane? I showed you here. PSE-PV membrane is perfluorosulfonyl fluoride ethyl propyl vinyl ether. Okay, so that is the monomer here. Okay, so how many TFE groups are present on in average is, if it is known, we can calculate the equivalent weight. So this formula is used. So that is practically a measure of ionic concentration within the ionomer. Typically, this electro equivalent weight for Naphtha membrane is around 1100. Although materials with equivalent weight as low as 700 have been synthesized and being studied. Okay, so even copolymers with equivalent weight of greater than approximately 1500 do not have ionic conductivity sufficient for the practical fuel cell applications, whereas this equivalent weight lower than 700 usually have poor mechanical integrity. That's why I even showed you here. So if it is more than 1500 equivalent weight, ionic conductivity is being affected. If it is less than 700, we are having poor mechanical integrity. That's why widely this 1100 is used, which has a good compromise between this ionic conductivity and mechanical integrity. So we have a fair ionic conductivity and mechanical strength when you use this Naphtha 1110. Okay. So if n values are given, these are some of the n values. Will you please calculate the equivalent weight in terms of 100? Just substitute this n value to get the equivalent weight. Okay, so that's what you will do. Now coming to the next property is, a membrane should take water uptake, right? So how we can get that one? The protonic conductivity of a polymer membrane is a function of membrane structure. Okay, So whatever is the water content in a membrane, that is usually expressed as grams of water per grams of polymer dry weight. It is like mass per mass unit. Okay. So that's what we do. Okay. So because this conductivity is a function of the structure of the membrane and the water conductivity. What is the water content that is available in the membrane, right? So that's what defines the ionic conductivity of the polymer membrane. Okay, so how much number of water molecules can be present per sulfonic acid group present in the polymer is given by lambda equal to n of H2O by n of HSO3 groups. Okay, so effect of state of water, you can see that how much water molecule can be present in the per sulfonate group when water is present in liquid form, or if water is present in the vapor form. Okay, here you get a clue for why it is preferred to operate at low temperature, why it is not favorable at high temperature. Okay, when you are operating at below the boiling point of the water, at least at the boiling point of the water, what you get is the maximum uptake of water molecule is around 22 molecules per group of HSO3 group. Per HSO3 group, there can be 22 water molecules that can be present. But once the vapor phase water is present, in that case, the number of water molecules uptake by the sulfonate group is around 14. So that way it drastically reduces when water becomes vapor. So that's why we want to operate it in liquid where you are going to have only boiled water in the system. Okay. Remember, the water uptake from this vapor phase may be more relevant for the fuel cell operation because the reactant gases are humidified and water is present in the vapor phase. So what happens is, you can see the water activity versus water uptake. As a graph you can see, what you observe is at the low vapor activity region, around A equal to A of water equal to 0.15 to 0.75, water uptake increases to about lambda equal to 5. You can see up to 5, up to 0.75, it is 0.8, you have 0.8. Up to here you can see there is a good increase, right? So it is increasing, lambda value is increasing up to 5 only. But at the high vapor activity region, around 0.75 to 1, the water in uptake rate, you can see there is a change in slope value, right? So there is a steep increase in water uptake, which is about 14.4. Okay. So this is observed at a temperature of 30 degrees Celsius. Coming to the protonic conductivity, the charge carrier density is an ionomeric proton conductive membrane of equivalent weight 1100 is similar to that of 1 molar aqueous sulfuric acid solution. So that is the equivalent, you see. 1 molar is how concentration, right? When in case of acid fuel cell, the charge carrier density of this proton conductive membrane is similar to that of the 1 molar sulfuric acid solution. Okay. So remarkably, this proton mobility in a fully hydrated membrane is only 1 order magnitude lower than the proton mobility in a aqueous sulfuric acid solution. So that is why we tend to use this type of membranes. So as a result, this protonic conductivity of a fully hydrated membrane is about 0.1 Siemens per centimeter at room temperature. Okay. So we have this equation K equal to, we can go through this as a function of temperature, how this lambda is, K is changing based on lambda. At low water contents, that is lambda is around 2 to 4, hydronium ions will be moving via the vehicle mechanism. As the water content increases, that is when lambda is increasing from the range of 5 to 14, there is a easier movement of hydronium ions is facilitated. And when lambda is greater than 14, water is in interfacial region screens weakly bound water from ion dipole interaction, and both water and ions will be moving freely. Okay, that's why you have this. So if you look at this, when lambda is 2 to 4, you can see this white dot represents water, gray represents H3O plus, dark black represents SO3 minus. You can see that when how the free movement of water takes place when lambda is greater than 14. Okay, so mechanism of water and hydronium ion movement through PFSA ionomer at various hydration levels, as such suggested by the scientist Savos Simki. So there are several mechanisms of water transport across a polymer membrane. Because water is produced at the cathode side as a result of electrochemical reaction. The rate of water generation is given by NH2O is equal to I by 2F, where I is the current density and F is the Faraday constant. Okay. And the electroosmotic drag and electroosmotic drag coefficient. What is this? Electroosmotic drag coefficient is defined as the number of water molecules per proton. Actually, in general, this coefficient is a function of membrane hydration, how much it is hydrated with water. Okay, so water is dragged from the anode to the cathode by the protons moving through the electrolyte, as described previously. This is called electroosmotic drag. It's like it is actually moving, it is picking up something else also. Actually, only H plus ions is supposed to cross through the membrane. What happens? This in the momentum, it is carrying the water also along with it. Okay. So that is called as electroosmotic drag. What is the flux of water due to this electroosmotic drag in moles per centimeter square is given by NH2O equal to the function of this lambda I by F, where this function of lambda is the electroosmotic drag coefficient. Okay, so it is defined as the number of water molecules per proton. Okay, so based on that you can get the flux of water. What is the flow rate of water across the membrane? That is flux. Okay. And this, what is that electroosmotic drag coefficient epsilon lambda? So the following linear relationship between the electroosmotic drag and membrane water content is proposed. So we have epsilon lambda equal to 2.5 lambda by 22. So it's a function of lambda. Okay, water generation and the electroosmotic drag will be creating a large concentration gradient across the membrane. And because of this gradient, we know that mass transfer, whenever there is a concentration difference, driving force will be established, right? So mass transfer will take place. So that way, because of this gradient, some of the water will be diffusing back from the cathode to the anode side, and the rate of water diffusion for that is given by molar flux, which is given by diffusivity into delta C by delta Z, which is nothing but your diffusion law. Okay, Fick's law of diffusion. Okay. What is D? Here D is the diffusivity. So it is a water diffusion coefficient in the number of water content, and delta C by delta Z is the driving force, dCA by dZ, right? Is the water concentration gradient along the Z direction in the membrane. Okay, so this ray D ranges from the 1 into 10 power minus 6 to 10 into 10 power minus 6 centimeter square per second. Okay. So that diffusion coefficient is again Fickian or interdiffusion coefficient of water through the polymer membrane D, and some correction is required because it is a Fickian water diffusion coefficient. That is a proper transport property to be used in the macroscopic studies of water. Okay, where if A is the thermodynamic activity of water, CW is the water concentration membrane, DS is the self diffusion coefficient of water. So then diffusivity coefficient or Fickian diffusivity coefficient is given by dou of ln A by dou of ln CW into DS. Okay. And this water concentration in the membrane can be given by CW can be given by rho m by EW lambda. What is that EW? It is equivalent weight. Okay. So there are reports which show d lambda value, that is diffusivity of water. Okay, so water transport in the Naphtha membranes, we have two values, two expressions are there. So if lambda value is given as 0 to 3, we will be making use of this equation. If lambda value ranges from 3 to 17, we will make use of this second equation. As a function of temperature, what is the diffusivity value? Okay, so these are taken from literature by Motupalli et al. Okay. So this is the diffusivity coefficient value to determine as a function of temperature. Lambda value is known. Okay. And what is gas permeability? Because gas permeation is important here, because these membranes has to allow the gases through pass through, right? Because the having the raw material reactant or product, if any one of them is in gas phase. So if you consider ideal case, this membrane should not allow any of the reactant gases or product gases or intermediate product gases to pass through the membrane, right? That is ideal case. They should remain impermeable to the reactant species. However, some of the gases do permeate through the membrane because there is essentially porous structure, it is having water content, and also there is some solubility of hydrogen and oxygen in water is can take place, right? And this permeability is a product of diffusivity and solubility. We know the solubility value and diffusivity value, multiplying them, what we get is the permeability. Okay, so permeability is given by the product of diffusivity and solubility. Both of them should be substituted in the given unit. So you have diffusivity in centimeter square per second and solubility in moles per centimeter cube. So the final unit of permeability should be combination of these, right? So moles per centimeter cube, centimeter square per second, then per Pascal. Okay, so that way the solubility you are having moles per centimeter square Pascal. Okay. So solubility is given by moles per centimeter cube per unit pressure. Okay, so that is Pascal. So this is the unit of permeability. PM equal to D into S. So solubility is unit is this, diffusivity is this. So together you can write like this. Instead of simply cancelling to simplified unit also you can write, just to understand it you can write fully, then you can cancel later. Okay. And permeability having the unit, why I have written as such is we are going to introduce another unit called as permeability unit, which is the bearer. Okay, bearer is the most common unit to express the permeability of a membrane. Okay, and if we know the V molar having the unit of centimeter cube per mole, one bearer equal to 10 power minus 10 centimeter cube centimeter second inverse centimeter per centimeter square centimeter mercury inverse. So if you write one bearer equal to 10 power minus 10 centimeter cube centimeter second inverse centimeters minus power minus 2 centimeter into Hg inverse, that is mercury unit. Okay. Now, if you want to convert this permeability unit into bearer, what you have to do is permeability equal to D into S multiply by V molar into, we have to convert this unit to 101.325 Pascal is equal to 76 centimeter mercury. So that way, this is centimeter mercury inverse, right? So that way, we divide by multiply by 101.325 Pascal by 76 centimeter mercury, we get this bearer unit. So that is the conversion factor. And also, we should know what is the solubility of hydrogen, because solubility is a function of, you can say that it is independent of temperature. For hydrogen, we can say at least. Okay. Whereas for oxygen, it is a function of temperature. It is given by the following equation. Similarly, diffusivity of hydrogen as a function of temperature, diffusivity of oxygen. Remember, we are going to mostly use hydrogen and oxygen for our numericals. So these values we will be making use when you do solve some problems. Okay. So you have solubility of hydrogen, solubility of oxygen, diffusivity of hydrogen, diffusivity of oxygen. These values we should know expressions. Once temperature is known, operating temperature, we will substitute the temperature to get diffusivity values. Okay. And solubility of hydrogen, oxygen. Hydrogen is same, right? It is independent of temperature. So we will use 2.2 into 10 power minus 10 moles per centimeter cube Pascal. Whereas this will make use of the function of temperature. Okay. And if you look at the permeation rate, which is given by flux of hydrogen across an area of a centimeter square and a pressure P kilopascals, we get flux equal to PMAP by D, where D is the thickness of the membrane, P is the pressure, A is the area. So permeability multiplied by area multiplied by pressure divided by thickness of the membrane will give us the permeation rate. Okay, so the permeation rate NH2, in addition to the permeability, obviously should be proportional to the pressure and the area of the membrane, and it is inversely proportional to the thickness of the membrane. That's what we see from this equation. Okay. So this equation we should know. Permeability we have seen, permeability is a product of diffusivity into solubility, and further if you multiply by area, pressure and divide by thickness, you get the permeation rate. Okay. And the permeation rate can be expressed in terms of current density also. So by if you know NH2, 2 times Faraday constant into flux, this permeation rate divided by current density A. Okay. current density is ampere per centimeter square. Okay, so this, when you divide by current density, you are going to get the relationship like this, okay, in terms of current density. So that you can rearrange to write, if current density is I, then NH2 is equal to I divided by 2F. I by 2F, which is when we given a rearrange to get small I equal to 2F NH2 by area. Here current density is current divided by area, right? Ampere per centimeter square, right? So this way you can write. So hydrogen has a 1 order of magnitude higher permeability than the oxygen, and this permeability to wet naphthalene is another order of magnitude higher, as shown in this figure. So that's what you can see through this permeability of hydrogen, oxygen, nitrogen for a naphthalene membrane. Okay, you can see how it is varying. At least it is a log graph. You have 10 power minus 11 to 10 power minus 10, 10 power minus 9, 10 power minus 8, like that. So you can see the gap between nitrogen, oxygen, and hydrogen. Okay. And what about the permeability of oxygen through this dried and hydrated naphthalene membrane? So you have dried membrane, different membrane is written, right? Numbers are there, N117, N125. Okay, so you can see the change in that also. Okay, so that's what we want to discuss about the naphthalene membrane properties. Now coming to summarizing the properties of this membrane, because we have seen what is the basics only. So if you look at the naphthalene membranes, they have just to forget about this other 2%. I took taken it from a literature report from Sivashankar and Sankita et al. Okay, so naphthalene membrane, that commercial naphthalene membrane, if you subject to a study, you will find out that their thickness are around 190 micrometers, and protonic conductivity is given by 2 into 10 power minus 3 s per centimeters, and oxygen diffusivity in centimeters square per second is 2.7 into 10 power minus 6. Okay. And another report from another paper, you can see that there are different naphthalene membranes, right? So naphthalene 112, naphthalene 1135, naphthalene 115, naphthalene 117. So that has been subjected to studies. We can see that the thickness is around 51, 89, 127, and 178. And their basis weight is around 100 grams per meter square, 190 up to, it is increasing when it increases. Okay. Because of the thickness, you can say 2 to 7, it is moving from 100 to 360. Okay. Now, coming to the physical properties again, what is their water uptake rate? It is around 35. What is that water uptake from a dry membrane soaked in water at 100 degrees Celsius for 1 hour? That is the amount of water take, percentage water uptake. Okay. Then tensile modulus is reported at 50 or percent relative humidity. You have when water soaked at 100 degrees Celsius, what is the tensile modulus is reported? You have tensile strength reported, all that. Okay, so these are some of the properties of the naphthalene membranes. Now, just going for a case study and just quickly summing it up. Already we have crossed time, so I'll just show you some of one of the researcher in our department, PhD scholar. So she prepared some of the membrane, composite membrane, and did some studies. Okay, so what are the it's like case study. What are the tests you have to do once you have prepared an alternative membrane for naphthalene, right? So that is the question here. So if you look at that mechanical strength, as I said, we have seen these are the properties. Obviously, we have to see, right? We have to note down these properties. How to do that only? I'm going to explain. Okay. So mechanical strength, how will do? There will be universal stress strain analyzer will be there. So in that you will, what you do is we take a sample membrane of 3 into 5 centimeters square and we keep it in the sample holder, and they conduct at a particular 1 kilonewton per minute loading rate. We conduct the experiment. So what is the maximum withstandable load for the membrane sample will be recorded. So the mechanical strength of the sample will be calculated using the equation mechanical strength equal to maximum load by cross section area into 100. Okay. So this procedure will be repeated for at least a minimum of 5 samples and the average value will be reported. Okay. So that way we will determine the mechanical strength of a membrane. Okay. Then what we do is to understand what is the content, different contents available in it. What we do is how we make use of a thermal gravimetric analysis, TGA, DTA, which is differential thermal analysis. These are more sophisticated. Earlier days, no, we have to stop the experiment and take it to know, keep it in a weighing balance to know the decrease in weight. Okay, I think in some of the UG laboratories for drying experiment, brick will be kept in wet brick. We'll keep it inside the dryer. We'll have a weighing balance. So with respect to time, hot air is going, which is drying taking away the moisture. So obviously the wet content of the brick, the weight will be decreasing, right? So that experiment you might have done in your mass transfer lab, right? Thermal drying experiments, wet brick or wet any biomass we take, then we allow it to dry, weight will be decreasing. So decrease in weight will be noted down, right? So here it is a highly sophisticated one. Same thing here. So you are going to have a weighing balance, but weighing is known manual thing. It will be automatically recording with respect to time. What we additionally do is we are changing the temperature from room temperature to very high temperature. Depending upon the material, you can go change the temperature. So what you will know is how the weight is decreasing. For example, up to 100 degree, you can say that decrease in weight is because of moisture content. Then up to 200, less volatile, means highly volatile material. After that, low volatile material, right? So like that. So that composition can be determined using this PGA, which actually in some other course you'll learn in detail about that also. So here what we make use of is a TGA analyzer can be used. What we do is the dried sample will be loaded into a alumina crucible and the analysis will be started. So the temperature at a scan rate, it's like increasing 10 degrees Celsius per minute. We keep increasing the temperature. So you know exactly every minute or every particular second, you note down the, which it is recorded, weight is recorded. Initially you have taken 10 grams. You won't take that much actually. 1 gram, let me say 1 gram is taken, or you can say 1000 milligram is taken. It will, with respect to time, it may go down to 800 milligram, 700 milligram, 600 milligram, like that, right? So how it is decreasing in weight will be calculated. So also you can do the differential thermal analysis also. Okay. Also even some reactions are taking place, right? When you are heating it at a temperature, what is the product being formed also can be analyzed if you connect a GCMS to the exit stream. Usually argon gas will be passed through it. So in place of that, if it is a inert, okay. So whatever is your product when it is burning above the temperature, you can note down the composition. So from the analysis, it's like flue gas analysis, you will be able to identify the composition of the gaseous stream that is leaving when you are heating above the temperatures, right? So that's why it can be done in this type of TG analysis. So membrane also you can do the same. Okay, so this is a typical photograph of TG analyzer. You just take only one small 1 milligram or 1 gram maximum of sample is sufficient to get accurate analysis of your composition also. Okay. So there is another thing is how it is stable to the oxidation. So what is the chemical stability of the membrane, right? So that chemical stability of the membrane in the oxidative environment of the fuel cell can be studied using Fenton's reagent. So in this, what they do is they take ferrous ammonium sulfate solution will be prepared by mixing it with some hydrogen peroxide solution, some ppm of ferrous sulfate also added, and mixing it at 80 degrees Celsius. So what they do, they dip 3 membrane samples, will be dried first at hot air oven because we want to remove the moisture content in it. So we know the initial weight. Then we will keep immersed into the 3 different beakers in which 3 membranes, this prepared solution will be kept. So once you dip that, and after 24 hours, take out the sample, and or you can say every 6 hours, you can take the sample out and find out what is the weight loss. It's similar to weight loss method, how we do, how much weight is lost with the time. Okay. So that way we do this thing. Okay. And as I said, whatever membrane we prepare, we compare it with the performance of the Naphtha membrane. Okay. And there is another property called ion exchange capacity, IEC. So the acid-base titration procedure will be employed to determine this ion exchange capacity of the cation exchange composite membrane. So what they do is the dry weight of the composite membrane sample will be measured. It will be conditioned for 12 hours in the 0.5 molar HCl. so that all the ion exchange sites are filled with the proton. So then the hydrated sample was washed using the distilled water, and again it is immersed in 0.1 molar NaCl for 24 hours, where we are replacing all the H plus ions with sodium ions. Okay. So the resulting acidic solution will be back titrated against 0.5 molar NaOH solution. Okay. And whatever is the volume of NaOH consumed to neutralize the acidic solution. Okay. That will be determined. So you can do the titration value once you know the molarity and you know the mass, you can get the ion exchange capacity using this formula. Okay. And what is the water uptake? Yeah, you can take a dry weight of the composite membrane will be measured before dipping it in distilled water for 24 hours. So the membrane surface will be wiped with tissue and weighed instantly to measure the wet weight. And whatever is the amount it is there, increase in weight, we can get it as water uptake percentage. Okay, so then proton conductivity. The proton conductivity of any membrane can be calculated using various thickness of the membrane resistance, and active area of the membrane. How we get this membrane resistance? By performing the electrochemical impedance spectroscopic technique. They determine the RM value. The protonation of the membrane can be done using in 0.5 molar sulfuric acid per membrane per pre-treatment. So then it is sandwiched between the platinum coated carbon electrode into carbon conductivity cell, and both compartments will be filled with equal volume of 1 molar HCl. So the cell will be connected to potentiostat and galvanostat, and that electron impedance spectroscopy will be performed between the range of 0.04 Hz to 1 MHz by applying 10 millivolt AC voltage. Then the proton conductivity can be calculated using this formula, sigma equal to L by RMA. Okay. Then coming to the methanol permeability calculation. Actually, we don't want methanol to cross over, but however, we should know how much methanol it is allowing, right? So permeability studies can be studied out in a cell with 2 compartments, where the equal volume compartments are partitioned by the membrane. The conditioned membrane was sandwiched between the 2 compartments. 1 molar methanol solution will be filled in one side of the compartment, and other is filled with the distilled water. So both the M and W compartments were kept under continuous stirring for maintaining the uniform concentration throughout the cell. The collected sample from the W compartment are analyzed, determine the methanol concentration. You can use UV spectroscope. Okay, so it's like you have a barrier. One side we are having methanol, another side we have pure water. There is a change in concentration, there is a driving force, there will be crossover of the methanol. What is that one taking place can be used to calculate the methanol permeability using the formula, where L is the thickness, P equal to L into VW. VW is the solution volume, W. A is the membrane active area, T is the time in seconds, because CW not CW at any time T. Okay, and Cm is there. What is Cm? It is the methanol concentration, molarity. CWT is the methanol concentration in W at time T, and CW naught is the initial methanol concentration in the W. Okay, so that is a water compartment. Okay, we would like to point out that these low temperature PEM fuel cells are at the forefront of the commercialization of the fuel cells, because they are having some very good properties of high power density. They can initially quickly start up. They have very good efficiency also. However, there is low temperature PEM fuel cells have some of the disadvantages, such as they have very low tolerance to of the fuel impurities. Okay, or complex reformer systems with CO cleanup are required. Okay. So the low quality heat generated owing to the low temperature operations, and requirement for the complex water management system to prevent the drying or flooding of the membrane electrode assembly is required. And if you are looking at high temperature PEM fuel cells, when they are operating in the range of 100 to 200 degrees Celsius, they can overcome all these issues, which will result in the increased efficiency and simplification of the system. Okay, so why we have to go for high temperature fuel cells? Because we are having some of the limitations with these low temperature fuel cells, particularly when you are operating at a low temperature like 60 to 80 degrees Celsius. These Naphtha membranes being used as the electrolyte and separator due to the several advantageous qualities. However, when you are using at these temperatures, these Naphtha membranes have some limitations, such as reduced carbon dioxide tolerance. They lower the performance, the humidification. There is high expense due to low temperature operation below the 100 degrees Celsius. Okay. So in the next lecture, we will discuss in detail about high temperature PEM fuel cells, which is being operated around 100 to 200 degrees Celsius. Okay. Well, in this lecture, we have discussed about the membrane properties. Particularly, we have seen in detail about what is an Naphthian membrane, what are the functional groups that is attached to it, what are the properties that needs to be addressed that a particular membrane should have, and if a new membrane is prepared, what are the tests that has to be performed. All that have been discussed. Also, we have seen the limitations of low temperature PEM fuel cells. In the next lecture, we will discuss about high temperature PEM fuel cells. Thank you so much for joining my classroom. Meet you in the next lecture. Bye-bye.